Hey everyone. When we try to understand how things move, we often get bogged down in the details, tracking every single force, every push, every pull. But what if I told you there's a more elegant way, a deeper principle that lets us see the big picture, a kind of ultimate shortcut? Well, let's dive right in.
Seriously, what if you could just look at a kind of map of energy and know exactly where something's going to go? That's not science fiction, it's one of the most powerful ideas in physics, and that's exactly what we're going to unpack today.
Okay, so let's start with a really basic idea. In physics, we talk about work. It's what happens when a force moves an object. Now look at this image. If we move something from point 1 to point 2, does it matter if we take the short, direct path or that long, winding, scenic route? Does the journey matter? And the answer is, well, it depends entirely on the type of force we're dealing with.
And that brings us to a very special class of forces, because for these forces, nature just doesn't care about the journey. All that matters is the starting point and the ending point.
We call these conservative forces, and the best example is gravity. Think about it. If you lift a heavy box straight up to a shelf, that takes a certain amount of work against gravity. But what if you push it up a long, gentle ramp to that exact same shelf? Well, turns out the work done against gravity is exactly the same. The path is irrelevant. It's all about the change in height.
Now, this is crucial. If the path doesn't matter, then the work must depend on some kind of hidden property of the locations themselves. It's like every point in space has a value assigned to it. Let's call it v for now. And the work it takes to get from one point to another is just the difference between the v at the start and the v at the end. Simple as that.
This simple idea has two huge consequences. First, as we said, the work only depends on where you start and where you finish. But second, and this is a big one, the work is totally recoverable. It's like lending out energy. If you move an object and then bring it right back to where it started, the net work done is zero. You get all that energy back, ready to be used again. Nothing is lost.
So, what is this mysterious value V? Well, it's time for the big reveal. This hidden value is what we call potential energy. And it's not just a number. It creates an invisible landscape, a sort of topographical map that dictates how everything moves.
So potential energy isn't some vague concept, it's a field. You can think of it as a map that fills all of space, and at every single point on that map there's a number that tells you how much energy is stored there. You know, a bowling ball held high up has a lot of stored potential energy. That same ball on the floor, not so much.
And here it is. This is the master key. This beautiful, compact equation connects everything we've been talking about. It tells us that the force, F, acting on an object is completely determined by the shape of that potential energy landscape, V.
Now, don't let that upside-down triangle scare you. It's called the gradient, or del. All it really means is find the direction of the steepest uphill slope. But see that minus sign in our equation? That means the force always points in the opposite direction. It always points down the steepest downhill path.
And this visual just nails it. The lines here are like contour lines on a topographic map, lines of constant potential energy. The force always points in the quickest way down the hill, perfectly perpendicular to those lines. It's really that simple. An object will always try to roll downhill on the energy landscape.
Okay, so we have this map, this energy landscape, and we have a rule for how things move on it. Now, let's see how this leads to maybe the most powerful shortcut in all of physics, the principle of conservation.
So let's imagine we're in a system where only these special path-independent forces, these conservative forces like gravity, are doing any work. When that's true, something absolutely beautiful and simple emerges.
And there it is. The total energy of the system, which we'll call E, is just the sum of two things. Its energy of motion, which is kinetic energy, or T, and its stored or positional energy, or potential energy, V. And here's the kicker. In this kind of system, that total value never ever changes. It's constant.
Just think about what that means. Energy can't be created out of thin air, and it can't be destroyed. All it can do is change forms. As a roller coaster plummets down a hill, its potential energy, V, drops, but its kinetic energy, T, skyrockets by the exact same amount. The total energy, E, stays perfectly, beautifully constant through the whole ride. It's the ultimate accounting principle.
Now, this isn't just a neat philosophical idea. It's an incredibly practical tool. It's a superpower that lets us solve problems that would otherwise be a huge headache. So, let's put it into action.
Right, take a look at this. How fast is this cylinder moving when it gets to the bottom?
Now, if you wanted to solve this with forces, you'd have to draw diagrams, worry about torques, calculate accelerations. It's a mess. But with our new energy shortcut, it's almost laughably easy. We just look at the beginning and the end. At the top, the cylinder is still, so it has zero kinetic energy, but it's full of potential energy. At the bottom, all of that potential energy has been converted into kinetic energy. So we just set the initial potential energy equal to the final kinetic energy. Solve for the velocity, and we're done. No forces, no mess. It's just elegant.
But hang on, the story doesn't end there. This idea of an energy landscape does more than just predict motion. It also tells us about balance and stability. It explains why the world is structured the way it is.
So let's go back to our rule. Force is just the downhill slope of the energy map. So what happens when there's no slope? A flat spot, right? Well, that's what we call equilibrium, a point where there's no net force. And on our map, these flat spots are the very bottoms of valleys and the perfect tops of hills.
And this makes the difference between the two types of equilibrium crystal clear. A ball resting at the bottom of a valley is at a minimum of potential energy. If you nudge it, it just rolls back. That's stable. But a ball balanced perfectly on top of a hill, that's a maximum of potential energy. The slightest breeze will send it tumbling down, never to return. That's unstable.
A simple pendulum is the perfect example of this. When it's just hanging there at the bottom of its swing, its potential energy is at its absolute minimum. That's its stable equilibrium point. But if you could somehow balance it perfectly pointing straight up, that's its point of maximum potential energy, totally unstable. And of course, there's a neat mathematical way to test for this. You look at the second derivative, which is just a fancy way of asking about the curvature of the energy landscape right at that flat spot. If the curve is shaped like a bowl or a smile, it's stable. If it's shaped like a dome or a frown, it's unstable. So let's just zoom all the way out for a final thought. We've seen how the shape of an energy landscape determines the stability and fate of everything from a simple ball to a pendulum. So that leaves us with a pretty profound question, doesn't it? What about the universe itself? Is it sitting comfortably at the bottom of a stable energy valley? Or is it balanced precariously on some cosmic hilltop, waiting for a push? Something to think about.